Dimensionless numbers are an important concept to understand heat and mass transfer. We're going to be using a pipe and a flow through a pipe in order to understand how we get to a dimensionless number with null space, and we'll use Python in order to find that null space. So if we draw our pipe, you'll see that it has several variables that we need to consider. The velocity of the compound going through, as well as its change in pressure from one end to the other. The length of the pipe is very important, and its diameter. Those two are very similar variables. The viscosity of the fluid flowing and the density of the fluid flowing are also important for this problem. From there, we can use a dimension matrix in order to do the first step of finding our dimensionless numbers. So our matrix, we're going to have units. We'll have kilograms, meters, seconds, and these units correspond to the units for our variables. So we have velocity, change in pressure, length, diameter, viscosity, and density. Our velocity is meters per second, and what this tells us is there is an exponent of 1 on the meters and an exponent of -1 on the seconds. If you rewrite that, it's m to the 1, s to the -1. And there's no kilograms. So you put 0 next to kilograms, 1 next to meters, and -1 next to seconds. Our change in pressure is in pascals. And pascals are in units, newtons per meters squared. Newtons are also in units, and those units are kilograms, meters, seconds squared. If you multiply that by our 1 over meters squared and cancel out the units that are necessary, you get kilograms per second squared meters. So you have a positive exponent on the kilogram and 2 negative exponents on the seconds and 1 on the meters. Our length is just in units meters. Our diameter is the same. Our density is just in kilograms meters cubed, but our viscosity is in pascals per second. Thankfully, we already derived the correct units for pascals, and so just multiply it by seconds and cancel out some of the units, and you get kilograms, seconds, meters. So let's put that into our matrix. Our length has nothing in kilograms, 1 in meters, nothing in seconds, so it is our diameter. Our viscosity has 1 kilogram, -1 meter, and -1 seconds, and our density has 1 kilogram, -3 meters, and 0 seconds. From here, you would typically multiply it by constants. These constants could be an infinite number of numbers. And we use this in order to find our dimensionless numbers, which have units of 0. Unfortunately, it's not easy to do without something like Python. And for Python, before we get into it, we have to understand what we're trying to find. So we have 6 variables, and if you subtract it by the 3 equations that are possible, you get our 3 constraints. And those 3 constraints, you can choose from our list of variables. It's a good idea to choose variables that cover all of the units. So all 3 variables should have, one of them should have at least 1 kilogram or 1 meter or 1 second. And we have 3 equations we're trying to find, pi1, pi2, and pi3. That's how we denote them. So let's write out those 3 variables that we chose. Our length, our change in pressure, and our viscosity. And then we also have the rest of the variables, our velocity, our diameter, and our density. Let's put length to the power of 1, pressure and viscosity to 0, and the rest of the units will get random letters, that we will find using the null space. Should also mention that null space is a vector, or vectors, 6 dimensions of them. Good thing to know. So let's continue. You'll notice a pattern really quickly. It's the exact same variables. Instead of length being to the first power, it's going to be 0 power, pressure is 1, and viscosity is 0. Instead of using A, B, C, we'll go down the alphabet, so D, E, F. And you should know what to do for the next pi. 0, 0, 1, and then G, H, I. Now we found all that we need to in order to find our null space in Python. Let's transition so we can find our dimensionless numbers. Google Colab is a great way to run Python in your browser, as well as find the null space numbers that we are looking for and the coefficients that we want to find the dimensionless number, pi 1, pi 2, and pi 3. First thing you're going to want to do is to import numpy as np and import scipy as sp. Run that so that works for the rest of the code. The next thing we're going to do is we're going to create our matrix, which is np array, not matrix, as you would think. Put 2 brackets in, we're going to do the first row of our matrix, and I'm going to rearrange it as opposed to what we did in writing. And instead of I did velocity, pressure, length, diameter, viscosity, and density. I'm going to rearrange it so that the variables with the fewest number of units are in the front and the most in the back, or like from left to right, least to most. So length and diameter, then velocity, then density, viscosity, and pressure. Our first row is kilograms, so our length and our diameter do not have any kilograms. Our velocity does not have any kilograms, but our density, viscosity, and our pressure do. Comma, next row, it's going to be our meters. Our length, diameter, and velocity have meters. Our density has a -3 and the rest have -1. And our final row, which is seconds, has none in length, none in diameter, -1 in velocity. Then we have none in density, then -1 in viscosity, and -1 in pressure. -2 in pressure, sorry. We'll run that, make sure that works. There we go, there's our array. So from here, we want to find our null space. So we'll label that NS. You can label it whatever you desire, but I think NS is a good choice. So we'll import our scipy. We'll do that for linear algebra and our null space for A. Make sure you're running everything. It's just a good indicator that everything's getting the necessary information it needs. I have done this before and it has gotten me the wrong do that. So let's run this, and there we go. Those are the correct numbers I have checked before. From here, we want to find our coefficient 1, or C1, and our C1, which we're going to use as a dot product, so we'll multiply that by our matrix. And our C1 is going to be numpy, import numpy, and we're going to do linear algebra once again. Our solver, this is where the solver came in. And then we're going to do our null space, and from our null space, we have 3 different variables we're looking for, and those variables are our length, our change in pressure, and our viscosity, which we earlier denoted as having exponents of 1, 0, and 0 for our pi, our Buckingham Pi method, where we said that these are the special 3 variables that we want to take out of the equation in order to find what the equation is actually going to be for our dimensionless numbers, and that's going to be 0, 4, and 5. Going to do comma, colon, and that colon says that we're going to go by each row. From here, we want to do our NP array, and we're going to say that L is 1, length is 1, and pressure 0, and viscosity is 0. Make sure everything is in order. I'm actually going to change some of these parentheses and add a period right there. Incorrect parenthesis. Where's that come from? Oh, there we go. We can delete one of these. So let's run that and then run our C1. These are the numbers you should get from there. We want to create the dot product from our null space. And that top product is going to get us these numbers. Now, what do these numbers mean? Well, it's a great question. As before, we talked about that Buckingham Pi method, and we had our pi 1, our pi 2, and pi 3. So each of these numbers denotes an exponent that goes to each variable: length, pressure, viscosity, velocity, diameter, and density. The first one is length. It corresponds to our matrix. So the first one is length. Oh, we don't want that. It's going to be ns. Let's see. So the first one is length, and that's going to be the power of 1. We'll say that it's pi 1. So length is to the power of 1. Our diameter is to the power of -1. And the rest of these numbers are so small that it's not really necessary to write them as an exponent because they're so teeny tiny that they're negligible. So the first equation is going to be our length over our diameter. We want to do this for the rest of our C's. So we have C1, now we're going to go to C2. And C2 is going to be the exact same setup, but instead of length being equal to 1, we're going to be making it so that length is equal to 0. And our pressure is to 1. Run that. Run this. Multiply that by our null space. And we get these numbers. So again, let's analyze what this says. It means length is no longer a part of this for our pi 2. Length is negligible. Our diameter is still -1. Then we have our velocity, and our velocity is -1. Our density, so our rho, that's going to be -1. Our viscosity, which is mu, that's going to be 1. And the pressure change is negligible. So our final equation is going to be the diameter times mu divided by our velocity times rho. And finally, our C3, it's going to be the last equation. Once again, it's going to be the exact same code, but we're going to change the 1 for the viscosity. Run that. Do the dot product with our null space and analyze. So our pi 3, we have that length and diameter are negligible, but velocity has the exponent of -2. Our, what's that? Our rho is to the -1 power. Our mu is negligible, our viscosity is negligible, and our pressure is to the first power, or change in pressure. So over delta P to the first power, which means that our equation is delta P divided by V squared multiplied by rho. And let me just edit this. This is actually, our diameter is going to be on the denominator. So here we have our final equations, our dimensionless numbers. None of these numbers have dimensions for our Buckingham Pi method for a pipe. So there you go. Now you figured out how to solve for a null space, which is a way to find a dimensionless number by multiplying it by a matrix that you came up with in order to find, again, a dimensionless number, or for the Buckingham Pi method, 3 equations, however many equations you need at the very least, that show you how to get a dimensionless number for a certain problem that you're going through. And this one is specifically for a pipe. So we've discovered how to create a dimensionless number for the flow of a pipe.